So welcome everybody to the talk by Dr. Oberai. Dr. Oberai is the Hughes Professor of Aerospace and Mechanical Engineering in the Viterbi School of Engineering at the University of Southern California. He earned a Bachelor's of Engineering degree from Osmania University in India in 1992, a Master's from the University of Colorado in 1994, and his PhD from Stanford University in 1998, all in mechanical engineering. He was an assistant professor at Boston University from 2001 to 2005 and Resler Polytechnic Institute in 2006. He moved to USC in January 2018 and was the Vice Dean for Research in the School of Engineering from 2019 to 2021. Dr. Oberai leads the Computational and Data-Driven Discovery CD3 group, which designs, implements, and applies data and physics-based models and algorithms to solve problems in engineering and science. Those problems include better detection, diagnosis, and care of diseases such as cancer, understanding the role of mechanics and physics in medicine and biology, modeling the evolution of multi-physics and multi-scale systems, and reduced order models for aerospace and mechanical systems. In fact, I attended one of Dr. Oberai's tutorials at the conference. He was basically talking about very complicated mathematical concepts, but in a very intuitive way, and I'm very happy that he accepted our invitation to give a talk today. I'm looking forward to his talk. So as you can see, basically, the applications of his work are very wide. Dr. Oberai is a fellow of the American Society of Mechanical Engineering, the American Institute of Medical and Biological Engineering, and the United States Association of Computational Mechanics. He received the National Science Foundation Early Career Award in 2005 and the Department of Energy Early Career Award in 2004. I can go on and talk about his bio, but in the interest of time, I'm going to give the floor to Dr. Oberai and thank him again for accepting our invitation. Dr. Oberai, I will be looking forward to your talk.
Thank you, Hassan. Thank you very much for your kind invitation and this chance to present some of our recent work. So I'm going to begin by sharing my screen.
Sorry, Dr. Oberai, sorry for interrupting. So if you have any questions, you can ask them at the Q&A after the talk. So there will be around 20 minutes time reserved for questions at the end. So you will be typing your questions and I will read them at the end. Sorry for the interruption.
Not at all. So like I said, I want to thank you for this invitation and the Perform Center for giving this opportunity to talk about some of our recent work where we are applying some deep learning methods, probabilistic deep learning methods to medical imaging. This is work that I've done along with my postdoc, Dr. Deep Ray, and 3 students, Saeed, Raghib, and Hari, and collaborators from the medical school at USC, that is Vinay Dudalwar's group and Daniel Pelletier's group. All right, so here we go. Here is kind of a brief outline of what I'm going to do. I will motivate some of the work that we have done, and I'll spend some time on that. Basically, I'll introduce 3 different classes of problems in medical imaging, and then sort of walk you through how I think they can all be formulated in one unified way, like with a single problem statement. And then once that problem statement is set, I will describe how certain deep learning algorithms, in particular deep adversarial learning algorithms, can be applied to solve that problem. I'll show you some of our recent results and very brief conclusions. If there are questions, like Hassan said, please post them on the chat and I'll be happy to come back to it. My plan for this talk is actually not to go over 35 to 40 minutes, so that I hope we'll have plenty of time for discussion afterwards. Okay, here we go. So the first class of problems I want to talk about in medical imaging is image segmentation. I think anyone who works in this area knows what this problem is, right? So the measurement, or the input, is an image of an organ or multiple organs. And what we desire to do with that, the desired image, is basically for every pixel that's in the image, you want to put it in a particular class. So whether it belongs to a certain organ or does not, or belongs to a different organ, right? And so there are lots of examples of image segmentations. It can be done at the organ level, or maybe at the level of sub-organ things like tumors, and you can apply it to CT, MR, ultrasound, PET, and so on and so forth, right? So here is an example of image segmentation, which is image segmentation applied to an MR image. So this is an MR image of the brain that contains the skull. It contains the eye sockets, the nasal passage, and of course the brain. And the idea or the goal here is to remove everything else but the brain. And so this is the segmented image, which only contains the brain, and the rest of the tissue has been removed. Now, what is hard about this problem? That it's hard in the sense that if you wanted to do this manually, it's tedious, and of course it's subjective. So some person might think a particular pixel or voxel belongs to one tissue, where someone else might think it belongs to a different organ. So, okay, so that's image segmentation. I'm sure you've all seen this before. Another class of problems is image imputation. So this is somewhat different. So what's the input here? The measurement. So the measurement here is, let's say, a sequence of incomplete images. So there's something that's missing. And what you need to do is the desired output is a complete sequence of images, right? So the examples here could be, you could have missing regions within an image, which are occluded for whatever reason, or you can have missing images within a sequence of images, right? So you imagine like a stack of an image of a volume, and you're missing a few slices there. The particular application that we are looking at is slightly different. So I want to motivate that with the few images down here. So what you see in the bottom row of images here are basically CT images of a kidney, taken axially. And so you can see the kidney in here. And these are contrast enhanced CT images. So the first image is a pre-contrast image before the contrast agent has been injected to the patient. And then you wait a couple of minutes and there is an uptake of the contrast agents by the kidneys, and you can sort of see things brighten up. And then you wait a few more minutes and you enter what is called the nephrographic phase, where different parts of the kidney light up, and the excretory phase where the contrast washes out, right? So these are 4 time points. So the problem we are looking at is, what if one of these time points was missing? So what's if you had only 3 out of these 4? Then, is there a way of imputing the missing image? So the difficulty here is that if you consider the missing sequence as the measurement, the desired quantity is the full sequence. And so that the map from the measured to the desired image is ill-defined. There can be lots of possibilities that could be used to fill that in, and that makes it hard to solve. The interesting observation here is the opposite map, which is the desired to the measurement, is actually really simple. So if I give you this sequence of 4 images here, it's very easy to delete one of them and create what would be a measurement, right? What would be the missing sequence. All right, so that's image imputation, another class of problems. And the final class of problems that I'm going to talk about or are going to apply our algorithms to is what I call field transformation. So here the input or the measurement is field of one physical type, and the desired output is a field of a different type. And usually it's a tissue property that you're trying to image. So the examples of this can be CT or elastography. I'll talk a little bit about elastography because that's the imaging modality I'm really familiar with, right? So in elastography, you would have, let's say, a subject with a tumor out here, and you have an ultrasound transducer that is sort of looking in that region, right? And you slowly compress the ultrasound transducer, and you acquire a sequence of images, ultrasound images here, and then you do image cross-correlation, and from that you can determine the displacement field, right? And now comes the map that I was talking about. So this is the measurement, And what you want to get out of this is a spatial reconstruction of a physical property, which is the Young's modulus of the tissue. So you want to go from here to here. So you want to go from the displacement field to the Young's modulus, right? And so what's the difficulty here? The difficulty here is that, again, this measurement to the desired map is ill-posed. And what I mean by that is, for a given displacement field, you can have, in fact, an infinite number of solutions of the Young's modulus. It's also unstable and so on and so forth. So that, there are issues with that. The observation to be made here, which apply to image imputation, also applies to this problem, is the opposite map, which takes you from the Young's modulus to the displacement field, is actually simple. So if I gave you this displacement, if this Young's modulus, and I told you what the loading conditions were, it would be relatively easy to determine the displacement field. All right. Okay, so these are sort of three different classes of problems that we are trying to solve. And what I contend is that you can sort of look at them in the same way. So what you're given is a field or a vector y. You think of this as an image, right? So this is the input. So in the case of image segmentation, it's the multi-organ image. In case of image imputation, this is the incomplete sequence. And in case of elastography, this is the displacement image. What you would like to do is you would like to find X, right, which is the output. So that's the single organ image or the complete sequence or the shear modulus in terms of elastography. So that's the problem statement. So this is fine, except I contend it's important to account for uncertainty. It's important to look at this problem in a probabilistic way. And why is that? It is because the measurement, as you all know, is always contaminated by noise. And a good model to model noise is usually a stochastic or a probabilistic model. So your input itself is probabilistic, therefore your output better be probabilistic. So that's one reason. Another reason why you might want to look at a probabilistic model is that in all these three problems that I talked about, a single measurement y may have many likely x that are appropriate. So in segmentation, if you're sitting at a pixel that's at the interface between two tissues, it could go either to tissue A or tissue B, right? So it's subjective. If you think about image imputation, there could be lots of likely images that fill that particular image in a sequence of images. And if you think about elastography, you can prove mathematically that for a given displacement field, there is an infinite number of solutions for the modulus field that are consistent with that displacement field. So for all these reasons, it makes sense to look at this problem probabilistically. So let's do that, okay? So if we look at it this probabilistically, what we are basically saying is y and x, so y, remember, was the input image, and x is the output image, are no longer deterministic quantities. They are basically random vectors or random fields. And then what we are trying to compute, or what we're trying to characterize, is the conditional distribution, which is p of x given y. So what we are saying is, if you give me an instance of the measurement y, I know that there isn't a single value of x. There is a distribution of different values of x that I'm interested in. More precisely, given the measurement y, what we would like to do is generate multiple samples of x that are selected from the conditional distribution. So that's the goal here. So all these problems can be written down as this probabilistic problem that you're trying to solve. Okay. You're trying to solve it, and that's great. So the question is, how do you create a model and then train the model in order to be able to solve this problem, right? And so what is the training data? What does the training data look like? Okay, so this is where these three problems sort of fall into two categories. So they diverge a little bit. So in image segmentation, if you think about it, it's pretty obvious how you're going to train a model in image segmentation. So what you would do is, you would, for example, think about the brain, think about the image of the head, right? You have the MR image. What you would do is you would take an image, a slice, and get someone to manually segment out the brain, right? And then you would have your output, which would be the segmented image, and then your input, which was the original image. And they would do it many, many, many times. And they would basically generate samples from the joint distribution P of X, Y. And you would have many such samples available, and then you can start to train your algorithm, right? So that's image segmentation. Now, in image imputation and the field transformation problems that I was talking about, things are slightly different. So let's talk about image imputation. How would you generate training data in this case? So what you would do is you hopefully have images where you have subjects where you have the entire sequence available. So what you would do is you would start from that. You would select this sequence from the organ that you're looking at. So if you're looking at kidneys, it would be, sequence of images acquired on the kidney. And then what you would easily do is just delete some of those, right? And create the measurement Y. So it's because the transformation from the desired map to the measurement is so simple. It's as simple as just crossing out some images, right? You would be able to create the measurement Y. And so for every XI, you would have a YI. Eventually, what that means is you would still have XI and YI that have been sampled from the joint distribution, right? So this is how you would create those samples. And the same approach applies to elastography also. So if you know you're looking for circular or oval inclusions, what you would do is you would generate shear modulus fields that look like circles or ovals, right? Then you would load them in a finite element code and compute the displacement corresponding to that, right? And then do lots of such samples, and you would generate these samples XI, YI from the joint distribution. So the point is, in all these three different types of problems, the input data is XI, YI from the joint distribution. How you get there is slightly different. Okay, so you have this, and now we can really complete the problem statement. So the problem statement is, given these samples from the joint distribution and a single measurement, Y, generate samples of X from the conditional distribution X given Y. So we're talking about generating not one image, but samples of image, right? Okay, so the problem is set, and now we want to solve it. So what are the challenges in solving it? So the first thing you realize right away, that the dimensions of these vectors Y and X are very large, right? So a typical image is at least 100 by 100, right? Sometimes it's 100 by 100 by 100 if it's in 3D. So you're talking about a dimension of 10 to the power 4 or 10 to the power 6. The other challenge is, if you think about the distribution that is formed by these vectors, Pxy, it's a very complex distribution. It's not Gaussian, it has none of those properties. So you're talking about really complex joint distribution. And finally, when all is done, what you want to be able to do is you want to be able to sample from this conditional distribution X very efficiently. So you want the algorithm to be relatively fast. So given all these challenges, what is a way to sort of overcome them? How do you go about solving them? So the techniques we've used fall into this class of deep adversarial learning, and sort of the network that implements those is called a generative adversarial network. So I'm going to now transition and talk a little bit about those techniques and then move on to the applications. Hassan, can you tell me how much time I've taken so far?
Around 17 minutes.
Okay, thanks. All right, so maybe I'll spend maybe 7 or 8 minutes just talking about GANs, and then we'll move on to the applications. Okay, so before I get to the actual network that we use, which is a conditional GAN, I need to explain just the GAN, which is a generative adversarial network, and then we'll move on to the conditional GAN. Okay, so simply stated, what a GAN does is it takes lots of samples that are sampled from a distribution Px, and what it does is it learns that distribution and also learns how to efficiently further sample from that distribution. And the way it does that is through these two networks. One is called a generator, the other is called a critic. So the generator takes a random vector Z, and Z has a really simple distribution, like Gaussian, for example, a normal distribution, and then maps it to the space of the output that you're interested in. So if you're interested in an image, it'll map it to an image. So inside this, there will be lots of convolution layers, there'll be ResNet layers, there would be nonlinear activations and all those stuff going on here, right? the output would be an image. And so it'll take lots of Z's and generate lots of fake images. And then, of course, you have the set of true images with you, right? And so the critic will take an image as an input and produce a scalar valued output. And it would take images from the fake set and images from the true set and produce a scalar valued output. And it wants to take images from the true set and assign a small value to it, and take images from the false set or the fake set and assign a large value to it, right? And so this can be expressed in a loss function or an objective function, where which is defined as you take images from the true set, pass them through the critic, right? And you take the expectation or the average of all of those and subtract from that all the fake images. So you sample Z from PZ, pass them through the generator, and then pass them through the critic, but assign a negative sign to it. So what the critic or the discriminator wants to do, it wants to maximize this objective function. It wants to increase the difference between these two sets as much as possible. And what the generator wants to do is it wants to fool the critic. So it wants to minimize this distance. So that leads you to a min-max problem that's given here, okay? And then you can show that if you're able to solve this min-max problem, then the fully trained generator network will have the following property, that if you take a Z that is sampled from the simple distribution PZ and pass it through the generator, that would be the same thing as sampling X from the original distribution, from the true distribution. So the GAN has basically learned the true distribution, and the generator provides you an easy means for sampling from that distribution, right? So this is a standard GAN. What we use is a conditional GAN, all right? And so just like GANs learn a distribution, conditional GANs learn a conditional distribution, which is what we are interested in, right? And so how do conditional GANs work? So now the data set that's given to you contains X and Y sampled from the joint distribution. This is the training data, right? Again, you have a generator. The generator takes the random vector Z, but in addition to that, it takes a measurement Y, and it maps it to the desired field, to the desired image X, all right? Now you take the true Y and you take the fake X and you construct a set of fake samples, fake pairs, Y and X's, right? And in addition to that, you have a set of true pairs, X and Y here. The critic will take each one of these and it'll assign a large value or a large real value to the true pairs and a small real value to the fake pairs, right? And so you can define an objective function, just like you can do it for GAN, you can do it for a conditional GAN, where you take basically the samples from the true joint distribution, pass them through the critic and take the average of that, and then take the fake samples by taking Z from PZ and a Y from PY, right? And then pushing it through the generator, and then taking the real Y and this pair and pushing that through the discriminator or the critic, and taking the average of that and assigning a negative value to this. So the critic will want to maximize this, will want to pull these apart, will want to be able to distinguish these two sets, whereas the generator will want to fool the critic. So it will try and minimize this. And when you're done with training, you can prove that sampling from PZ, from that simple Z for a given Y, sampling from PZ, and then passing it to the trained generator with that value of Y, right, with that value of the measurement, is the same as sampling X from the conditional distribution. So the generator has learned the conditional distribution, and it gives you a means to sample from that distribution, right? And so that's basically exactly what we want, right? And sampling is easy because the space Z has a much smaller dimension than the space X. And then the generator is very efficient that in that the forward propagation hardly takes any time. So you can generate lots of samples of the likely value of the likely image for a given measurement, right? So the generator allows you to do that. So once we generate all these samples, what do we do with them? So now, we have an ensemble of likely solutions or likely images. What we do is we compute statistics of these. So we compute a mean image and we compute a variance image. The mean image is our best guess at whatever it is that we are looking at. And the variance image tells us pixel-wise regions where we are uncertain about our guess, right? And so not only do we produce an answer, we also produce a means to be able to say how confident we are in that answer. Okay, so I'm going to move on. Oh, before I move on, there's one more thing I want to say. The architecture of the generator plays a really important role. For those of you who've looked at these things, are familiar with this, the architecture is basically a U-net. And what that means is that the input and the output are linked to each other at multiple spatial scales. So you sort of, you drop down, you start with the finest scales, you keep going to the coarsest and coarsest scales. And then the output and the input are linked to each other through these concatenation networks at multiple scales. And then in addition to that, we introduce randomness, right, through this latent vector Z. So the latent vector Z also plays a role at multiple scales. So it determines, roughly speaking, the intensity and then the amplitude of the fluctuations at multiple scales. And since it's a random vector, what that means is that the intensity and as well as the amplitude of the fluctuations are themselves random quantities. All right, so I'll stop at that, and happy to talk about this at the end of the talk. Okay, I think I should move on to some applications that now describe how all of this works. So I'm going to start exactly with the three applications that I started with, that I began this talk with, which is segmentation, imputation, and then elastography. All right, so let's look at segmentation first. All right, so the measurement in this case is an MR image of a slice of a skull with a brain in it, and then other organs, right? Could be like in this image, you can see the eyeballs, and you can see the eye socket, you can see the nasal passage, right? And what we would like to do is create a slice which only has the brain in it. So that's the problem we're trying to solve. And so how do we generate the training data? So there is this data set which basically contains MR images, slices of MR images of 125 subjects that have been manually segmented. And so you have the corresponding image of only the brain, right? So this is the skull, this is the brain here. This is again, sort of the image of the head. And now this part is only the image of the brain, and so on and so forth. This is a section that's taken further up in the head, and this is the corresponding brain, okay? So there is 125 such subjects that are in this data set, and we take 75 for training, and then we retain the other 50 for testing our algorithm. Okay, so once the algorithm is trained, what we have is this generator, right? The input to the generator is going to be a full-blown image, right? An image which contains the entire head. And hopefully the output is going to be an image which only contains the brain, right? And there will not be one output, it'll be an ensemble of outputs. We will take the average and display that, and we'll take the standard deviation of pixel-wise standard deviation and display that, right? So these are some of the representative results that we get. So the left column here is the input. You can see that this is a slice that's sort of further up somewhere here. So you can see sort of the skull appears to be thick because you're taking an oblique slice. You can see the meninges, right? And in there is the brain tissue that you're interested in. This is the target because this is a validation testing sample. We know what the right solution is. And this is basically, these two are the outputs of our algorithm, right? Our algorithm produces many images. We compute the average, that gives us the mean, and we take this as our guess. So you compare this with the target and you see it's really close. And this is the standard deviation. So this is the quantification of the certainty. And so this is telling us we are mostly very certain inside the brain and outside the brain, but on the boundaries, there are a few pixels where we are uncertain, where it could be one or the other, right? And that's a feature you will see over and over again. Now, here's another slice, which is further down, maybe somewhere here, right? And again, the target, this is the mean. This is our guess at what the solution ought to be. And once again, the standard deviation, the pixel-wise standard deviation. And once again, this is telling us we are most uncertain at the boundary. We are pretty certain inside the brain and then outside the brain. And here is a challenging slice because this is like somewhere here, just below the eyeballs and above the nose. So you can see the nose and the nasal passage quite clearly. You can see the sinuses. And then, here is the target. And this is the mean that we produce, right? And again, it's really close. And again, most uncertainty is on the boundary, right? So we can be much more precise about the performance of this algorithm. And these are sort of bar plots that demonstrate that. In this, I'd like you to focus only on the, BET-R, which is a brain extraction tool, which is clinically used, and CGAN, which is basically our approach. So ignore the first and the fourth columns in each of these, focus on the second and the third. What we're plotting here is for all the test data, right? We're plotting the dice similarity coefficient of the segmented image. And of course, we know the benchmark in this case, right? And so for BET, it is around 0.92, the average value. That's what this bar denotes. And these whiskers denote the range. Whereas for our approach, it's around 0.98. So a pretty high dice coefficient. And you sort of see the same trend in the positive predictive volume. The best you can achieve is 1. We get to about 0.97, whereas this BET tool gets to about 0.87, and the same for sensitivity and volume ratio. So in terms of quantitative metrics, also this approach seems to do well. Okay. I do want to talk a little bit about what is the utility of quantifying uncertainty. Like we produce, like for every input image, so here's an input image, right? We produce, like I said, we produce many outputs, and then we take the average and display that. That's what this is. And then, of course, we display the pixel-wise variance in our ensemble, right? And that's what this image is. So in this case, if you focus on this region down here, where the rectangular box is, you notice we've taken, our algorithm actually thinks that this is a part of the brain tissue, whereas the expert thinks that this is not a part of the brain tissue, right? And this is all coming from here because, this is really close to this, right? And so it's included here. But if you look at the standard deviation, that's exactly where the standard deviation is high, telling us that's exactly where our algorithm is most uncertain. So that's basically a warning flag to anyone who's looking at our results that, we think this is the brain, but we are really uncertain about it. So watch out, right? So you can imagine that could be useful to someone who's using this as a tool downstream. There is another thing that you can sort of, a more average metric that you can get out of the standard deviation. So for every volume, for every subject, right, we generate the entire volume, and then we calculate the average standard deviation predicted for that particular subject, right? We also calculate the volume dice error for that subject because we know the exact solution in this case, right? This is test data. And then we plot them together. And what we find is wherever our confidence is low, or our variance is high, right? That is, our confidence is low. That's exactly where we commit. That's exactly the subject for whom we commit the largest error. So why is this useful? This is useful because again, imagine you're taking this tool and applying to a case where you don't know the right answer, right? But it gives you a large value of variance. Then that should be a red flag in saying that, please, don't trust this answer very much. You need to do something more to improve your answer. Okay. All right. So this was, application to image segmentation. Now, the application of exactly the same algorithm to image imputation, right? So here, the measurement is a sequence of incomplete renal images, contrast-enhanced renal images with tumors in it. And what we would like to do is complete the sequence of these images. And in order to generate the training data, we had CECT images from complete CECT images from 450 subjects with malignant and benign tumors, renal tumors. And then, we basically took this and just, deleted one of those time points, right? CECT images are acquired at 4 time points. So this is the entire sequence going from top to bottom. We deleted one of those time points and created the measurement, right? And so we created lots of pairs like this and used that to train the algorithm. And now the input to the algorithm is going to be an incomplete sequence, and the output will be the complete sequence with the imputed missing time point image as part of that sequence. Okay, so let's see what that looks like. So this is by far a harder problem to solve than the segmentation problem, right? Because we are literally trying to create a brand new image where no image exists based on whatever can be learned from all the sequences that are available to this particular algorithm, right? So this is one subject, right, where we actually know all the 4 images. So we know all 4 time points, but we purposely say, okay, we don't know the first, the pre-contrast time point, but we know the corticomedullary, the nephrographic, and the excretory time points. We know the CECT images there. In this case, by the way, there is a tumor right here. I hope you can see my cursor. That's where the tumor is, so that when the contrast is supplied to it, the vasculature there is disrupted, and you can see a pretty heterogeneous pattern there. It doesn't light up all together. Some parts light up and some parts do not light up when the contrast gets there, right? Okay. And so the goal is to construct the pre-contrast image. So the input to our algorithm are these 3, and the output is lots of guesses at what that pre-contrast phase would look like. We take the mean and we plot the mean of those images here. So you can see the kidney here, right? This is the mean, and this is the true mean. So what the algorithm has done correctly is recognize that that the pre-contrast image has to be lighter than all these 3 images. It's got the shape of the kidney right, and if you compare with the true image, it's got some of the fact that the contrast within this has to be uniform. It's got that right too. But outside the kidney, it has created these artifacts, and that's room for improvement, I would say. Okay. Now we do for the same subject. We now say, okay, we have the pre-contrast image, but we are missing the corticomedullary time point. So we are missing this time point, and we have the other 3, right? So given these 3, can we reconstruct this image? And once again, we construct lots of images and take the mean of that and display the mean image here. And right next to that is the true corticomedullary image, right? And here you notice that the algorithm has correctly recognized that the bright patterns are towards the periphery of the kidney. That's what you see in the true image, as well as the reconstructed image, and the fact that where the tumor is, you should not have a high uptake of the contrast agent, right? And that's what you observe in the true image as well. So it's got that right. And then maybe I'll just show one more. And so this is, we are trying to impute the nephrographic phase, which is this phase, given these 3 images, right? Here is the true image, and here is our best guess at the true image. And once again, it correctly sort of brightens up the periphery of the kidney and leaves the tumor as being heterogeneous and not bright. Okay. Yeah, I think we have a similar thing for the excretory phase, but there's nothing more new to say there. So I'm going to move on to the final application, which is in elastography. So remember, this is a kind of a field transformation problem where we are measuring one field and we want to go to the other field. So the field that we are measuring here is the axial component of the displacement, right? So you basically have tissue, you're compressing it, and you're measuring the displacement in this direction. And what you want to recover from this is the spatial variation of the shear modulus or the Young's modulus of the tissue. All right, so how do we create the training data for something like this, right? So the cool thing about this is the training data in this case is purely synthetic. It is created using a mathematical model and does not require any measurement at all, right? So the way we do that is, so if you tell me that you're looking for a tumor that is roughly, let's say, circular, right? What we do is we generate modulus images, likely modulus images of a circular inclusion, which is stiff, in a background which is soft, right? And we let the radius of this circle vary within a range, and we let the contrast vary within a range, and we let the location of the circle of this inclusion also vary within a range, right? And so we generate lots of samples of these likely modulus distributions. For each one of these, we solve the forward elasticity problem. So we load it and then solve that problem using finite elements and determine the axial displacement component, which is what this is, and then add noise to it, right? So this is X, this is what we want to get, and this is Y, this is what our measurement will be. So elastography system in the lab will measure the displacement, and from that we want to get to this, right? So, but in creating this training data, we start with X, which is the modulus distribution, and then we solve the forward problem, which is we compress it using finite elements and then get the displacement and then add noise to it. And these are 4 samples out of 8,000 that were used to train this algorithm. And then we apply it to real data that's measured in the lab. So this is data that is for a tissue phantom, right? So it's made out of agar and gelatin. And the phantom is actually a stiff circular inclusion in a soft background. And this is the displacement, the actual displacement that is measured, right? You can sort of see the imprint of the inclusion in here. So this is the input to our algorithm. The output is an ensemble of likely modulus distributions, right? So we take all of those and compute the mean. And so this is what the mean modulus distribution predicted by our algorithm looks like, right? It clearly shows a circular inclusion with a given contrast and you know, with a given location. And in this case, since it's a tissue phantom, we know the exact values of the stiffness of the background as well as the inclusion. And so we are within about 20% of that value. And in terms of the location and the radius, we are within about 5% of the true value, right? And it's interesting to look at the standard deviation. We are most uncertain about the boundaries of this tumor, right? So we don't know where that is. And then we are also uncertain about what the modulus is inside the tumor. And that's because the inside of the tumor, inside of the inclusion, the inside of the inclusion is stiff. And if I were to change that stiffness a little bit more, that will change the displacement by a very small amount, right? On the other hand, if I'm sitting outside of the tumor, which is soft, and I change that stiffness by the same amount, that will make a big difference in the displacement because it is soft to begin with. So even a little bit of additional stiffness will make it much stiffer than what it used to be. So the sensitivity is much higher in the soft region than it is in the stiff region. And that's exactly what the standard deviation plot tells us. We are much more confident about our prediction in the soft region than we are in the stiff region, right? That's what this is telling us. Okay. So this is work in progress. I think we are looking at more complex shapes and seeing if we're able to predict those as well. And that really brings me to the end of this talk. I think what hopefully I've shown you is how a particular type of deep learning algorithm, probabilistic deep learning algorithm called conditional GAN, can be applied for several applications in medical imaging, segmentation, for image imputation, and even transformation of different fields. And the cool thing about it is that it's a probabilistic algorithm. So it predicts the value, but it also gives you an estimate of the uncertainty. It can represent really complex distributions and leads to a simple sampling approach by which you can generate lots of likely solutions. And then, of course, once you have the estimates of uncertainty, you can use them for different tasks. You can say, well, should I really look at this segmentation and say this is a true segmentation, or do I need to have another look at it and do something else? Are there regions within this reconstructed image where I can be more certain, and regions where I really have to pay more close attention, and so on and so forth. And then we are looking at other probabilistic tools to solve these types of problems. Finally, like to obviously thank my sponsors, the Army Research Office, the Ming Hsieh Institute at USC, and AIER also at USC. So thank you for your time. I'm happy to take questions.
Thank you, Assad, for the very nice and very educational presentation. So there's already 5 questions, and since we are Dr. Oberai has to leave at 1 exactly, so let's start with the first question. So the first question is from Sobhan. So he's asking, what's the necessity of having Z, the random input, for the segmentation problem? Can't we just train the generator between pairs of input masks? And did you find CGAN better than GAN for image segmentation?
Really good question. So I hope, Sobhan, that through the example that I showed you of segmentation, I have probably half answered your question, which was this one, right? So you will not be able to do this, the utility of quantifying uncertainty. You will not be able to do this if you did not have Z as an additional input, right? You would for a given input, you would get only one output, and that's it. Now, how are you sure whether that's a good output or not a good output? Are there regions within this image where you might have made a mistake? All that information will not be available unless you treat this as a probabilistic problem and say that for a given input, there are multiple outputs. And that's basically the extra information that it gives you, and that's the reason why having Z is necessary. A comparison with the case where Z is not there at all, like a traditional cyclic GAN or whatever you want to call it, we are actually doing that right now. My take on that is, if we can perform in terms of accuracy as well as that, I'll be happy. I don't want to perform better than that, because the real utility of using a conditional GAN is this estimate of uncertainty that it gives you. So in terms of its accuracy, if it can sort of compete with, the algorithms that are already out there, I'm okay with that. But the utility, like I said, is in computing the uncertainty.
Yeah, so I have a quick follow-up to that question. So uncertainty is very important. And in fact, in our lab, we have used test time augmentation to find uncertainty, right? So you basically apply some transformation to the input, and here is it's a convolutional neural network, let's say a segmentation neural network, not a GAN. So you run it for, different inputs, that are like added noise or rotated a little bit, or you do dropouts during test, right? So did you compare, this like CGAN method versus, convolutional, like just a segmentation CNN for generating the uncertainties?
No, so you're absolutely right. There are other ways of generating uncertainty. Certainly dropout is one of them. No, so we haven't done that. I guess what I wasn't sure about with dropout is sort of the theoretical underpinnings, whether I would be able to prove the same thing, right? So with the conditional GAN, at least you could say for perfect training and enough amount of data and a network that is rich enough, you can prove certain things, right? That it will learn the conditional distribution. I wasn't so sure whether I could actually prove that for the 2 algorithms that you mentioned, Assad.
Okay, all right, thank you. So next question is from Ali, actually 2 questions. So the first question is, was the stress fixed in generating samples for elastography? So I guess it's about the image of the phantom that you showed, that you calculated the displacement. I think the question is, did you know the force?
Yeah. No. So it was not fixed. We sort of applied different values of in this case, we actually applied displacement boundary conditions on the top. So clearly that generated different values of stress. So that was not fixed.
So in the next slide, as a quick follow-up, so where you have, where you apply this to, a phantom experiment, do you know the force? How do you measure the, shear modulus, the exact value, not the, relative value?
Yeah, it's a really good question. No, so we don't, and so we can only, determine everything up to a multiplicative constant, so when I say we are, 20% of the true value, what I mean is 20% of the true contrast between the inclusion and the background.
So next question is from an anonymous attendee. Thanks for the great presentation. For segmentation application, I have two questions. First, I was wondering if you had compared your results with vanilla unit, your segmentation mask outperform unit in terms of dice score. So the first question is, in terms of not the uncertainty map, but the segmentation mask itself, does it outperform a vanilla unit?
Yeah, it's a good question. So we didn't do it ourselves. And given that there are so many questions about this in this talk, I feel like maybe we just ought to go back and do it. It's pretty simple. All we have to do is, from our net UNet, basically remove the contribution from the latent vector, right? Which is using conditional instant normalization, switch that to batch normalization, and we can do it. But we did compare with other people's work on this problem, which is called the brain extraction problem. And I think we compare with the best results that are out there, which is about 0.98 dice similarity coefficient. So I don't think we're doing better than that, but I also feel like at 0.98, you really don't have much room to do better. And so maybe we should really apply to a much more challenging problem and then really determine whether it's better or not. But I would like to reiterate, my goal, I don't think would be to try and beat those vanilla networks. It would really be to demonstrate that this computing uncertainty helps in better utilizing your output.
Yeah, I mean, the other point is that you mentioned that at 98%, there's not much to, improve. So there's also the issue of inter-subject and intra-subject variability, right? So sometimes if you give it to two different radiologists, they don't agree on, what is the boundary.
Yeah,
so that's probably as good as it gets, 98%.
Yeah, you're absolutely right. Like in some of these cases where we've got it wrong, we've like zoomed into the regions where we got it wrong. And I would almost contend that our algorithm has done a better job than the expert in those regions, right? But that's you're sitting on that threshold, basically.
Yeah. In fact, I have firsthand experience with that. We showed the results to, the radiologists. Sometimes they hesitate to say that, this seems to be better, right? So the second question is usually training GAN. So it's a continuation of from anonymous attendee. Training GANs is tricky and sometimes very hard. I would like to know, based on your great results, would that worth to use GANs for segmentation instead of simpler segmentation networks?
Yeah, I think so. I get this question a lot because I think there is this general belief, and I think quite rightly, that training GANs is not easy. But I would also like to point out not all GANs are created equal, right? So we are using Wasserstein GANs. Those are generally better beasts to work with. And then we are using a gradient penalty term that also helps in the way sort of training proceeds. And then we keep very close tabs on the Wasserstein distance as reported by the critic. And then also, you can sort of keep track of. So here's what, this is especially true for conditional GAN. So this would not be true for a general GAN, right? So for a conditional GAN, right, when you have when you have your data, you've kept some for validation, right? In those cases, it's a pair of Y and X. So for that given Y, the true X, right? And then your GAN is also producing, for that given Y, it is producing lots of X's. So you have that also. So you can actually keep track of that error, right, between the predicted X and the true X, and see how that changes as your training proceeds as a function of epochs. And we found sort of keeping track of that, and then choosing your hyperparameters to make sure that that decays smoothly is a good way to train these conditional GANs. Once again, this would not be possible for a traditional GAN, right? Because there, for a given Z, you will get some X. There is nothing to compare this X to. But of course, if it's a conditional GAN, you have a Y and a Z, then you will get an X, and you know what the true X is, so you can actually track this error, and you can tune your training process to make sure this decays fast.
Thank you. So the next question is from Sepide. So the question is, thank you for the great presentation. How do you introduce the order of the images to the network? So like, you have multiple channels as the input. I guess the question is, does that order matter? Yeah,
so we introduce, if I understand this correctly, you're probably must be talking about the image imputation problem, because there we have, right? Yeah. Because there we have a sequence of images, and does it matter how you introduce this? So we do introduce them in an ordered pair, right? So the first pre-contrast, then cortico, then the nephrographic, and then the excretory phase. So we certainly order it. The question then is, does the order matter? In this case, I would say not, because there are only 3 images. We don't do 3D convolution, for example, right? Because there are only 4. And on the other hand, if I had 50 such images, right, I would certainly use 3D convolution, and then the order would play an important role. Yeah.
And the follow-up question to that is that, like in the case of the CT images, I think the time difference, is not exact. Sometimes it can be like 10 seconds, sometimes 12 seconds. So is it robust to that? To the differences in the times that images were collected?
Yeah, it's a really good question. It is not, and it is not seconds, actually. It is minutes, and so that makes things even more difficult, because things change pretty dramatically from one instance to another. So this is a hard problem. So it's not like the same problem as saying you have a stack of slices and you're missing 5 or 6 in that stack. That is a relatively easy problem to solve. This is a hard problem to solve, and in the meantime, the patient has moved, right? Certainly over whatever 10 minutes or so, they could move quite appreciably. Furthermore, the patient has moved, and the relative position of the organ has shifted too. So all that sort of clinical complexity is in this data set, and we don't do much to sort of get rid of it. We use it as is, and we basically rely on the fact that we are using a probabilistic algorithm to handle all of that, right? Which again comes back to my point of saying that for a given missing image in the sequence, there isn't one answer which is good. There is a distribution of answers that might be good, which account for that variability, that the time point may not exactly be 1 minute, 20 seconds, it might be 1 minute, 5 seconds. And so that's yet another reason to actually do it in a probabilistic way rather than in a deterministic way.
Thank you. So the next question is also from Ali. So he's asking, what finite element software did you use for the forward problem? The design of the phantom in softwares such as Abacus is difficult and time consuming to have 8,000 samples to train.
These were 8,000 samples, but they were also very small problems. We used something called Phoenix, which is an open source finite element software that's available. I would highly recommend it to anyone who's listening to this talk. And so, yeah, so that's what I use. Before I leave, I want everyone to know that, if you want to get in touch with me, please send me an email. Please don't worry at all about whatever bothering me or anything. I'm happy and excited to answer questions via email. So my email address is aoberai@usc.edu. So that's my first initial, then oberai@usc.edu.
So Assad, there are two more questions. Do you have to go, or do you have
I can
one
maybe
more
take
minute?
another minute or two and quickly try and answer those. Yeah.
All right, thank you. So the next question is from Professor Grova. So he's asking, thanks for the great talk. Can you please clarify why L provided by the critic should be as large as possible and not as small as possible between the artificial samples and the real one?
And so it's both, right? So it's a min-max problem. So the L really is measuring the discrepancy between through the discriminator, the discrepancy between the true samples and the fake samples. So the discriminator would want to get better at spreading those two things apart, right? So that's why the discriminator is trying to maximize this quantity, whereas the weights of the generator will be determined by getting these things to be as close as possible to each other. So that's why the generator is trying to minimize it. So that's why you end up with a min-max problem, which is actually a really hard problem to solve. And that's basically the main problem with GANs, right?
I see. And the follow-up question to that is, have you compared this approach with hierarchical Bayesian modeling and associated sampling strategies?
Yeah, not in this context, we have not, but we are applying the same approach to solve physics-based inverse problems. There we are trying to do a more rigorous analysis. Okay,
so let me know, Dr. Oberai, whenever you absolutely have to go. It's 1 and 2 minutes.
I'll take one more question and then I'll bail.
Okay, so since Ali already asked 2 questions, I will move to Surena. So the question is, many thanks for the nice presentation. Regarding results using MC dropout for UQ makes the output highly correlated for each other and makes the UQ very hard. I'm not sure what UQ refers to. Do you know?
Uncertainty quantification.
Oh, okay,
so,
okay.
Yeah, right. So Surena is right? I mean, there are, I think, pros and cons between, let's say, the dropout approach for doing uncertainty versus using GANs, which is what we do. But we don't do MC dropout, Surena, to answer your question. So we don't run into that problem. We do run into the problem of training a GAN, which is not easy, but we have some ways around that. And I also do want to say, in some cases, we found that the variance that the GAN actually predicts is sometimes much narrower than the variance that is truly seen. So, which is consistent with what you just said, that you see that in dropout. We also see it sometimes in training the GANs. And usually, one way of getting around that is to use a larger dimensional latent space.
Thank you very much. There's one more question, but I know that you told me you really have to go at 1 and it's already 3 minutes past. So Ali, you can email Dr. Oberai for your question. So again, thank you very much, Dr. Oberai, for the very nice and engaging presentation. I learned many things, so thank you again.
Thank you.
And hope we can invite you in person soon.
I'd love that. And thank you very much. And then I'd really like to thank all the attendees and especially everyone who sort of asked a question. I thought, it was really nice for me to sort of get that feedback. So thank you.
Yeah, thank you guys for the great questions. So thank you, everybody. Bye. Have a good day.
Bye.